Hi there. Today I'm going to talk about my efforts to model the microwave emissions of snow on sea ice on a Pan-Arctic scale using a Lagrangian approach, and this is more or less the basis of my PhD. You can see the current situation in the lower right hand side of this slide. The model's running and I'm currently in data analysis mode and tuning some of the parameters. The backstory to this project is encapsulated by a Lagrangian snow model that already exists, called Snow Model LG. Lagrangian models don't use a static, regular grid like the rectilinear ones you may be familiar with on maps. Instead, they consist of many individual cells that move with the sea ice. For Snow Model LG in my model, we use the Polar Pathfinder ice motion vectors to move the cells around. This approach has a few distinct advantages. The first is that gradients in snow distributions can be maintained to a much higher level. On the right of this slide, you can see the fine spatial structure in snow depth, shown by Snow Model LG. Another advantage is that the stratigraphy of the snow in each grid cell is well defined. This allows the modelling of the snow's microwave emissions. First, I want to quickly show some of the parcels or cells that get advected around. On the right of this slide, you can see 1 in every 200 parcels as they move around the Arctic. I'm currently only running the model in the growth season between freeze up and melt onset, but even in that time I get about 60,000 tracks per year. Unlike Snow Model LG, my implementation with Snowpack has a sea ice component that thermodynamically grows, can generate negative freeboards and simulate the accompanying flooding. The sea ice component is also useful as it improves the realism of the heat flux through the snow to the atmosphere. Snowpack includes a relatively advanced treatment of grain metamorphism, and you can see from the top right hand plot that we observe the development of complex stratigraphy including melt forms, faceted grains and depth thaw. It looks like this flow experiences flooding around the middle of January and some snow ice formation. The most novel part of this project, however, is probably the linkage to SMRT. Every instance of Snowpack is linked to an instance of SMRT, and the output of the physical snow model drives the microwave model. At the moment, I'm just running in passive mode and outputting brightness temperatures. On the right of this slide, you can see the 37 GHz vertically polarized channel that's used in some snow depth retrieval algorithms. But in future, there's no reason in principle why the model shouldn't run in an active mode to simulate radar backscatter coefficients or even altimetric return waveforms. So what are the challenges of this approach in its current state, but also for the prospective radar mode? Roughness is a significant one. There's currently no incorporation of sea ice or snow roughness into the model. I'm working on a separate stream of research developing a simple Lagrangian model for roughness, and please do send me an email if you'd like to chat about that. It's based on the integrated history of the convergence experienced by an ice parcel. The physical snow model, Snowpack, also has no dynamical thickening mechanisms. In real life, sea ice experiences ridging and rafting during ice convergence, and my model doesn't account for that. When the sea ice converges, the cell's area just gets smaller and remains level ice and retains level snow. It's also important to be aware that I'm simulating the brightness temperature of the snowpack and not that measured by a satellite radiometer. We know that in the higher frequency channels of radiometers, like the 87 and 91 GHz, we do see the effects of heavy rain and thunderstorms. Radiometers of course also see gaps in the ice, and that affects the brightness temperature measured by the satellite instrument. I've also encountered some problems with the properties of new snow. When snow falls, its initial density on the snowpack surface is modelled to be very low, at less than 50 kg per metre cube. This seems like that's particularly being determined by a multilinear regression that was calibrated for alpine snow, but in the sea ice case, snow is almost always more dense than this. That touches on another issue, which is that when snow appears over sea ice, it's often not that it's fallen from above, but because it's been redistributed laterally from another part of the flow. That's an extremely difficult process to model, and it's not captured in these 1D parcel advection-based models. That begs the question of how representative these modelled stratigraphies are of their broader area and of their grid cell. I'm hoping to get some insight into this from the results of the Mosaic expedition. But if you are interested in these Lagrangian models for sea ice, then please do send me an email or a tweet, and thanks for listening.